Welcome everyone. Today, we dive into the fascinating world of physics. We start our journey with the triumphs of classical mechanics. This framework, born in the 17th century, was the brainchild of scientific giants like Sir Isaac Newton, whose laws of motion and universal law of gravitation laid the foundation for centuries of scientific exploration. Classical mechanics was a robust and reliable map for navigating the physical universe. It was our guide to understanding the dance of planets in their celestial ballet, the ebb and flow of tides, the fall of an apple from a tree, and the flight of a projectile. All these macroscopic phenomena could be predicted with astounding accuracy using Newton's laws. And it wasn't just about moving objects. The laws of thermodynamics, another pillar of classical mechanics, helped us comprehend the behavior of heat, energy, and work. They explained steam engines, refrigeration, and the basic principles that underpin the Industrial Revolution. In essence, classical mechanics was the language we used to converse with the universe, to ask it questions and decipher its answers. And for a long time, it seemed there was no question it couldn't answer. It was a deterministic world, where the future and past were simply the result of the present. It was a continuous world, where quantities like energy, momentum, and position could take on any value, not just some discrete ones. But as we neared the end of the 19th century, cracks began to appear in this seemingly unassailable edifice. There were phenomena that stubbornly refused to conform to the predictions of classical mechanics. It was as if the universe had started speaking in a language that our classical dictionary couldn't translate. And so, as we approached the 20th century, classical mechanics began to falter. It could no longer explain everything. The crisis was at hand. But remember, every crisis is also an opportunity. This one was no different, paving the way for a new understanding of the universe. A quantum leap in our knowledge, if you will. But that's a story for the next scene. Our first stop on this journey is the realm of blackbody radiation. Picture this. You're heating up a piece of iron. As it gets hotter, it starts to glow, first a dull red, then a bright yellow, and finally a dazzling white. This is blackbody radiation in action, the emission of light from hot objects, a phenomenon as old as the universe itself. Now, classical physics had an explanation for this. It suggested that the light emitted by a hot object like our piece of iron should form a continuous spectrum. That's a bit like a rainbow, a smooth transition from one color to the next, with no gaps or jumps. This continuous spectrum was based on the idea that energy, the stuff that makes light, could take on any value, no matter how small or large. But here's the rub. When scientists took a closer look, they found something quite different. Instead of a continuous spectrum, they saw a discrete spectrum. That's like a series of separate colors with distinct gaps in between. This was a shock, a contradiction of the established order. The observed reality was at odds with the predictions of classical physics. Enter Max Planck, a German physicist with a revolutionary idea. Planck suggested that energy doesn't come in a continuous flow, but in discrete packets. He called these packets quanta, and said that the energy of each quanta was directly related to the frequency of light it produced. Planck's idea was radical, even heretical. It flew in the face of classical physics, which held that energy was continuous, not discrete. But it explained the observed discrete spectrum of blackbody radiation, something that classical physics couldn't do. And so, Planck's quantum theory was born, the first step on the road to a whole new understanding of the universe. Classical physics could not explain this. The first cracks in the edifice were showing. Next, we turn to the photoelectric effect, a phenomenon that further challenged classical physics. Picture this. When light shines on a metal surface, electrons are ejected from that surface. This is the photoelectric effect. Classical physics, with its continuous wave theory of light, predicted that the energy of these ejected electrons should depend on the intensity of the light. More light, more energy, right? But the reality was a head-scratcher. Experiments showed that the energy of the ejected electrons wasn't determined by the light's intensity, but rather by its frequency. No matter how dim the light was, if its frequency was high enough, it could knock out electrons with a surprising amount of energy. Conversely, even the most intense light couldn't budge an electron if its frequency was too low. This was a conundrum classical physics couldn't solve. Enter Albert Einstein. In 1905, Einstein proposed a radical solution. He suggested that light wasn't just a wave. It was also made of discrete packets of energy, which he called quanta, now known as photons. According to Einstein, when a photon hits an electron, it transfers all its energy to the electron in one go. Hence, the energy of the ejected electron depends on the energy of the individual photons, which in turn depends on the light's frequency. This was a bold leap from the classical view. Einstein's explanation neatly resolved the photoelectric effect puzzle. It also provided further support for Max Planck's idea of energy quanta, earlier proposed to explain blackbody radiation. So what was the fallout? Well, the photoelectric effect was another nail in the coffin for classical physics. It revealed that light had both a particle and a wave nature, setting the stage for the concept of wave-particle duality, a cornerstone of quantum mechanics. Yet again, classical physics fell short, the cracks widened. Our final experimental stop is the atomic spectra, a world of discrete frequencies. In the early 20th century, scientists began to notice something peculiar about the light emitted and absorbed by atoms. When they passed this light through a prism, instead of seeing a continuous rainbow of colors, they saw distinct lines. Each element had its unique pattern of lines, or spectrum, much like a fingerprint. This was quite a surprise, as classical physics predicted a continuous spectrum of light, not these distinct lines. The Danish physicist Niels Bohr stepped into the ring to tackle this conundrum. He proposed a model where electrons in an atom couldn't just have any old energy. They had to occupy specific energy levels. The electrons could jump between these levels by absorbing or emitting energy, but the energy they absorbed or emitted was restricted to the difference between these levels. And here's the kicker. This energy was carried away or brought in by light, but not just any light. The frequency of this light had to match the energy difference between the levels. This explained why atoms only emit and absorb light at certain frequencies. They're not being picky, they're just following the rules laid out by the energy levels in the atom. In Bohr's model, the atomic world was not a continuum of possibilities, as classical physics would suggest. Instead, it was a place of discrete energy levels, a place where certain values were forbidden. This was a radical departure from classical physics, which was all about continuity and smooth transitions. But as we've seen, the atomic world didn't care much for the rules of classical physics. It played by its own rules, and those rules involved jumps, not smooth transitions. This atomic spectra, this world of discrete frequencies, was another nail in the coffin of classical physics. The edifice of classical physics was crumbling. A new paradigm was needed. Enter quantum mechanics, the new kid on the block, ready to revolutionize our understanding of the universe. As the 20th century dawned, the landscape of physics was transformed. The limitations of classical mechanics had been laid bare, and a new framework emerged to tackle these shortcomings: quantum mechanics. This was no minor adjustment to the established order, but a paradigm shift of epic proportions. The godfathers of this revolution were an extraordinary group of scientists. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac were among those who dared to venture into the unknown, their pioneering work laying the foundations for our modern understanding of the quantum world. Quantum mechanics introduced a whole host of novel concepts, upending many of our cherished notions about the nature of reality. One of the most fundamental of these was quantization. Instead of a continuous range of possible values, as in classical physics, certain physical properties, such as energy, momentum, and angular momentum, could only take on discrete or quantized values. This radical idea was the key to explaining the discrete spectra observed in blackbody radiation and atomic emission. Then there was wave-particle duality. Quantum mechanics proposed that particles could also exhibit wave-like behavior, and vice versa. This concept opened the door to a new understanding of the photoelectric effect, where light, behaving as a stream of particles or photons, could knock electrons out of a metal surface. And let's not forget the uncertainty principle. This groundbreaking notion, formulated by Heisenberg, posited an inherent limit to the precision with which certain pairs of physical properties could be simultaneously known. For example, the more precisely the position of a particle is known, the less precisely its momentum can be determined, and vice versa. These concepts were not merely abstract musings of theoretical physicists. They provided concrete explanations for the phenomena that had confounded classical physics. The quantization of energy could explain the discrete spectra of light emitted by hot objects and atoms. The wave-particle duality of light could account for the photoelectric effect. And the uncertainty principle, while unsettling, was a necessary consequence of the quantum nature of reality. Quantum mechanics represented a seismic shift in our understanding of the universe. It was a bold leap into the unknown, a departure from the comforting determinism of classical physics. But it was a leap that was necessary to make sense of the experimental observations that defied classical explanations. In the end, the proof of the pudding is in the eating. Quantum mechanics, with its strange and counterintuitive ideas, was able to explain the phenomena that had brought classical physics to its knees. It offered a new lens through which to view the universe, one that brought us closer to the truth of how things really are. Quantum mechanics had arrived, offering explanations where classical physics could not. So what did we learn from this journey? We've seen how the robustness of classical mechanics, with its deterministic and continuous values, held sway over our understanding of the universe for centuries. It gave us the tools to predict the motion of planets and understand the dynamics of falling objects. Yet, as we approached the late 19th and early 20th centuries, this seemingly invincible theory began to falter. The Blackbody radiation problem was the first crack in the armor. Classical physics predicted a continuous spectrum of light emitted from hot objects. However, what we observed was a discrete spectrum. Max Planck, with his revolutionary idea of energy quanta, offered a solution that defied classical physics. Then came the photoelectric effect, where light hitting a metal surface ejected electrons. Classical physics was at a loss to explain why the emission of electrons depended on the frequency of light and not its intensity. It was Albert Einstein who came to the rescue with his concept of light quanta, or photons. Lastly, the atomic spectra showed that atoms emit and absorb light at specific frequencies, contradicting the prediction of a continuous spectrum by classical models. Scientists like Niels Bohr championed the idea of an atomic model with discrete energy levels, once again challenging the continuous nature of classical physics. These experiments, and the contradictions they revealed, led to a paradigm shift. Quantum mechanics emerged, introducing concepts such as quantization, wave-particle duality, and the uncertainty principle. The explanatory power of this new framework was superior, successfully accounting for the previously unexplained observations. The impact of quantum mechanics has been profound, influencing fields such as material science and electronics, and reshaping our understanding of the universe at the atomic and subatomic level. It's an ongoing journey, with current research probing deeper into the quantum realm, promising exciting discoveries and developments. Quantum mechanics, born out of the crisis of classical physics, continues to shape our understanding of the universe. What will it reveal next? Only time will tell.